we make it easy for you to comprehend all what you desire to learn from our channel. Please, before we go on, I'd like to subscribe, share, comment, and tell others about this. And any advice you have for us is very welcome. Thanks to others who have been doing that, and we appreciate all. Today we are studying scalars and vectors. The study of scalars and vectors is very important in science, engineering, technology, mathematics. It's very important. And we'll go into the difference between vectors and scalars to show you how important it is to have full knowledge about vectors and scalars. It enhances your comprehension about anything in physics, mathematics, or engineering. Now, let's go. What are scalars? Scalars are physical quantities that can be described only with magnitude. That you need to describe with magnitude only. Magnitude or size only. Okay. What are the things that we refer to as scalars? Like mass, temperature, distance, speed, energy, etc. But vectors, for you to describe vectors very well, you will need to add to the size direction or sense or sense. So physical quantities that can be described only with magnitude and direction. Sometimes you can say with or without sense, because in showing the direction, the sense can be easily identified. And what do you mean by sense? Either in the positive direction or the negative direction. Now let's see. Scalars. If I tell you I weigh 25 kg, I don't need to tell you which direction my size is. But if I am telling you the force on me is 25 Newton, I have to tell you the direction by which the force is coming from, either from my back or from my right or from my left. So those are the things that you use to differentiate between scalars and vectors. So let's see examples of scalars. Here we have distance. So this is the space occupied. You don't need to show me the direction. So if somebody moves like this, 4 units and 5 units here, you can easily say the distance moved is 4 plus 5, 9. But in vectors, we have what we call displacements. So if you are going to talk about this, you need to say, okay, he moved 4 units to the east, to the east, and then 5 units to the south. You have to specify the direction. So at the end of the day, they will ask you, what is the displacement covered? The displacement covered is this, and the direction is this. That is it. So you have to specify the direction for vectors. So let's look at other examples of scalars and vectors. Let's look at this. You can say something like mass. This one is, now we say mass Another we talk about temperature, yes. We talk about energy, etc. Here we can talk about velocity, acceleration, momentum, etc. So anything that you will need to describe with the direction along with the size Those ones are referred to as vectors. As scalars, you don't need to specify the direction. Now, how do we represent scalars and vectors? When we want to represent scalars, we just write the sign and probably the units along with it. E.g., I can say for mass, I can say 36 kg. For energy, I can just say 576 joules. But for vectors, I have to say something like 76 meters per second and specify the direction if it is 50 degrees and whatever. And so that makes the addition, subtraction, or any other algebraic process on these two differ. If I want to add scalars, I can just do the normal algebraic process. Like if I have something that weighs 36 kg and another thing that weighs 75 kg, how do I add them? I will just say 75 plus 36 kg, 111 kg. That's how I add the scalars. These are scalars. But let's look at vectors. Since I have to put the direction into consideration, the addition is in geometrical form. Let's see how do I mean. Look at these vectors now. I have someone moved like this. 2 and 3 meters to the east. And data moved 4 meters to the north. The total displacement will be, you see, this one is east, this one is north, will be this. And that is using Pythagoras theorem. That will be square root of 9 or 3 squared plus 4 squared. And that is 5. So that is 5 meters. So I have to specify this angle as well. And that will be arctan 4/3. So if I want to write the resultant of this one too, I'm going to say it's going to be 5 and then put the direction, which I have to find using my table. That is the theta. So that is the major difference between scalars and vectors. And most of the time in our sciences, especially physics, mechanics, and any other thing like that, we use vector quantities. Only in few cases, that's why we use scalar. Most of the time, we use vector quantities. And that is what makes it very important to study this vector as scalars as topic. Now, most of the time we represent vectors by using arrow. And the size of the vector, we use the arrow to the size of the arrow to represent the vector and the direction. So, or we just have an alphabet like this and put arrow on top. So those are the major ways we use to represent vectors. So vectors will always have arrow around it to show that it is a vector quantity. Now, let's talk about resultant of vectors. Resultants. We use this word in relation to vectors. And what do we mean by resultants? Resultants is when we add different vectors and we are trying to find one single vector that will give us the same effect in size and direction as all the other vectors that are acting at that point or together, that we are considering together. Let me give you an example. If I have a body like this and a force is applied like this, another force is applied like this, I will have to look for one single force that will have that same effect that these two forces will have, and that is the resultant. So resultants can be considered as a single vector which will have effects as and can easily replace collection of vectors. Why? Because it has same value or size as the total vectors acting together and the same direction as the total vectors have. So what are we saying here? That this resultant is going to have the same effects as all these other vectors will have, and it will act in the same direction. That at the end of the day, if you allow all these forces to act together, that is the direction they will tend to. So this value of size, we refer to them as magnitude most times. So we can talk about vectors having magnitude only, and scalars having magnitude only, and vectors having magnitude and direction. I will give you an example of this resultant. Now, if there is a tug of war now, okay, this one goes this way, this one comes this way, and these people here, they are applying 100 Newton. These people here are applying 80 Newton. At the end of the day, we will say, okay, this one, we believe this one will win. So the force here now can be replaced by saying the total force at the end of the day is 20 Newton acting towards this direction. That is the resultant. We can easily do this because they are parallel. Now, let's look at another force. We have this one here. Let's call this one 8 Newton. And we have another force. Comes like this, 15 Newton. You know, this one is dragging towards this place. This one is dragging upward. At the end of the day, we are going to have a single force that will drag towards this place and at the same time drag upward. And what will be the value of the force? It's going to be something like this. And that is what we have. It's going to be 15 squared plus 8 squared. That is square roots. The leader should be 17. And the direction will be half tan 15 over 8. So I've given you brief illustration of how we get resultants. And resultant is very easy to get. You can use graphical method and you can use a geometrical method. You can draw, maybe. So you can draw. You can draw the forces using scale, like this one now. You can draw and say, okay, there is one force like this, 8 Newton, and there's another one here, 15. You represent these two here, and then you just join this place here, and you use your ruler or whatever to measure from this point to this point, and that is your resultant. Now let's talk about the analytical method, because most times this will take time and will not be that accurate. So in that one, you need the use of your table and your skill, your knowledge of trigonometry. But most times we need to use our sine rule, cosine rule, and any other rule in trigonometry. is very, very important. To be very good in this, to be sound in it, you really need to study your trigonometry very well. So you need to have good grasp of trigonometry to understand addition of vectors. Now, let's look at the analytical method. I've explained the graphical method using drawing the vectors to scale and then finding the resultant just by measurements. Now, let me explain if we use the analytical method. We have two rules that we use, the parallelogram law and the triangle law too. Now, what do we mean? Let's look at if we have two forces acting at, let's say, this is theta, this is F1, F2. Now, I want to add these two forces. What do? We will represent them using the side of triangle. So, we represent them using the side of triangle. What do? The first vector we want to represent, we will take one side of the triangle. That's F2 now. Now, this other one, you can see how it goes. Just like when you were doing your bearing. You will now draw this one to subtend this angle here. And then, this will now be your F1. You will now draw from the beginning, from the tail of the first one to the tip of the second one. You will draw an arrow. That is your resultant. You know this angle now is theta. This place will be 180 minus theta. And what do you do to find your R? Use your cosine rule. R squared is equal to F1 squared plus F2 squared minus 2 F1 F2 cos 180 minus theta. So you can see how easy it is to get this. So it depends on the angle. Depending on the angle, you will get your resultants. And sometimes you can easily use our parallelogram law too. Parallelogram. You know, parallelogram is just combination of two triangles. So, what do we do with this? We just draw this one, F1. We draw F2, and theta will be here. So, what? So you now draw the full complete parallelogram. You draw this side to be parallel to this one, F2. And then this top will be parallel to this one, F1. So, the sum, the resultant, will just pass through like this. That is the resultant. And you use the same formula to get it, because at the end of the day, this place will still be. So that is all about the addition or resultant of vectors. You know, I talked about sense the other time. When you want to do something like subtraction of vectors, we just turn one to the opposite side. How do I mean? If you have vector P moving towards the east, and we have a vector in parallel form with the same magnitude moving towards this place as Q. In vector notation, it means that P is equal to minus Q. Because they are parallel but in opposite direction. Parallel, equal, but in opposite direction. If you look at it, if P goes like this and Q comes like this and they are the same size, at the end of the day, you have zero vector. That's what it means. So when you want to do something like difference of two vectors, you might say subtraction. So what do we do about that? As I was explaining the other time, when we have to say find the relative, the one vector relative to the other, what they mean is subtraction or difference. I try to show you that if we have a vector in this way as P, and another one comes like this Q, but they have the same magnitude, but different direction, parallel to each other, they are equal but in opposite direction. So P can be referred to as minus Q. So how does this apply to our subtraction? You know, when we are doing this addition in our normal mathematics, this number line, thank you, this number line, you have, if you want to add, like I have 5 here, I want to add 3, I just do like this, it goes this way. If I want to subtract, I come like this. So since I can see the difference, that I can get opposite of this one now, it makes the difference or subtraction of vectors very possible and easy. Now, let's see what I mean. Like the other time I said, we have two vectors like this. We have F1, we have F2. And in my analysis, I need to see, to get the difference of the two vectors. One vector relative to the other. Like say, F1 minus F2 in vector form. What do I do? You know this is positive F. I will have to drop another one down like this. In the opposite direction, but equal to F2. So this one has come here. It has the same magnitude as F2, but minus. So if I want to find F1 relative to F2, what do? I draw F1 like this. If I want to use parallelogram law, I will draw F1 minus F2. And then I will now draw this one. This one. So this one will be parallel to this one. This one will be parallel to this one too. You know, this is the angle between them. Now, this will be the resultants. This will be the difference. And with this, I can find the direction here. I can find the direction here. Or I can say, okay, from here, depending. If this one is horizontal, I can find the direction. Anyway, you can find the direction. So that is all about the difference. I can also use your triangle rule too. This is F1. I have F2 down like this. F2 now come down like this. So now I just draw this one. So this is the difference. So we use it in so many analysis, and I know that as you work further, you will get to know more about this. Now let's talk about addition of more than two vectors. Let's say I have like 4 forces at a point. This one is F1, you can see the direction, F2, F3, and then F4. And I want to find the resultant of this. The only way I can do it is to take it 2, 2. What do? I will take this one and this one, find the resultants. After finding the resultant of these ones, I will add this one again, find the resultants. After finding that, I do this. So let me illustrate it. Now this one is F1. See the angle. Theta 1, theta 2, and then theta 3. The first one is this. Let's look at, if I add this one to it, I will go like this. See the sum. Can you see? Now again, this is theta 1. The next one, see, theta 2. Sorry, this is F2, F3. So, I will have to do that, F2, F3. Now, again, Can you see? So this will now be R1, R2, the R final. That will be my final resultant. So if I am going to use analytical method, I have to do it one by one. If I'm going to use drawing or graphical method, I'm going to do it one by one. And so, if you really look at this, with our knowledge in sign rule, the proving of all these sign rule and whatever, you can easily decipher something. If I want to get this one, we have something we call Pythagoras theorem, and it's something they have been using for a long time, which is very easy. Just add 2, square, and then you get the square root of the sum. Now, this R here now, I can get it by doing this. This is F1 in this direction. That is F1 sine theta. Look at this one too. So, please forgive me. This one is F1 cos theta. Again, look at this one too. This place is F3 cos theta 2. This one here too, look, and I bring it down, is F4 cos theta. Now, the components of this one now, F1 cos theta 1, F2 cos theta 1, F3 cos theta 2, F4 cos theta 3. I look using these angles here. And then, in the vertical direction, F2 sin theta 1, F3 sin theta 2, you can see. So this one is equal to this one, F1 sin theta 1. From here to here, F2 sin theta 1, F3 sin theta 2. You can see. So, when I added everything, you see F1 plus F2 cos theta 1 gives me RH. For F1, I don't have anything in the vertical direction. So I have 0 plus F2 sin theta 1, F3 sin theta 2, F4 sin theta 3, RH. So with this, it is very easy using Pythagoras theorem to get R. So R equals to RH squared plus RV squared. That is the vertical and the horizontal components. And direction is tan minus 1 RH over RV. So that's how we got it. And this has simplified the process of addition of vector and whatever. That leads us to resolution of vector. Resolution of vector is not just about addition or subtraction of vector, but in so many situations, you will need the resolution of vectors along axis. Now, what do we mean by resolution of vectors? It is separating, it is breaking into parts. When we look at vectors, just like any other, even like just like scalar, let me do this straight. If I have 8, I can break it down to 2 plus 6, 4 plus 4, 5 plus 3. In the same way too, I can have a vector v in this direction. So, I can use p in certain direction plus q in another direction too. It can give me v. Let me see like this. This is v. Now, I can use this one and this one. Let's say this is v, this is p, this is q. In the same way, I can say r m. But what do? We try to make things easy for ourselves in physics. So we resolve along 2 perpendicular planes. We resolve along 2 perpendicular directions. So we have 2 perpendicular directions, and this makes it easy for us to even apply Pythagoras rule. How do I mean? If you have a vector like this, let's say you have vector v in this direction, and we want to resolve it, we are going to draw 2 axes, and we are going to break it down along these 2 axes. So at the end of the day, the square of this plus the square of this is going to give us the square of this. Now, if v is acting in the angle theta up, I want to resolve it. Just like the last one I explained, addition of more than 2 vectors. What do we do here? This one will be v sine theta, and this one will be v cos theta. So it makes working on vectors very easy. And with this, I can easily add even up to 100 vectors. All I just need to do is know their direction and then break them along the same axis. Break them along the same axis. Take turns of adding the result vectors, the components along the axis. Let's see what I mean. Let's say I have vectors P, Q, R, S, and they are like this. They are in this direction. This one comes like this. This one comes like this. This one comes like this. Okay. This one also comes like this. And I have this one as theta 1, theta 2, theta 3, and theta 4. I can make the angle to this place too, but I believe you know what I mean. I just explain it. So this one is V1, V2, V3, and V4. V2, V1, V4, V3. And I am to add all this. I'm not using PQR now. I'm going to add this. I will look at the axis I'm going to use. So normally we use the axis along the right direction and upward. We use that along the right direction or upward. You can say I, J, or X, Y. So let me just make it H vertical. Yeah, let me just make it vertically upward. And so please don't mistake with the notation for the vectors. So if I want to add this, all I need to do is to say the direction towards these places for V1 will be horizontal and vertical. So V1 to the right will be V1 cos theta 1. To the vertical is V1 sin theta 1. V2 now, you can see it is in the opposite direction. It goes to the opposite direction. But this is our positive direction, and this is our positive direction. So for V2 now, I'm going to have, this is negative here, minus V2 cos theta 2. And it's still upward. I have V2 sin theta 2. You can see, we have to consider the sense, the direction. Now, V3, what do I have here? You can see it is downward and to the left. So I have V3 is negative now. Minus V3 cos theta 3. And here it is still downward. Minus V3 sin theta 3. You can see. Now let's look at V4. V4 acts towards the right, which is positive, but downward, which is negative. So on the horizontal, V4 is going to be V4 cos theta 4. And to the vertical, I'm going to have minus V4 sin theta 4. So look at R. So the sum of this, summation of VH components, that is what this place is for. And this place is summation of the vertical components. Because this, each breaking of it, this one is components. We break it into components. You understand? We resolve it into components. You resolve into components. That is what we do now. So at the end of the day, to find our R now, we are going to make it R will be equal to square root of summation H squared plus summation V squared. So that is our R. For the direction now, we are just going to make it arctan summation of the horizontal of the vertical components over summation of the horizontal components. So with this, once you know this, you can easily undo any vector. I mean any vector Everything is built on this. Now, let's see application of the resolution of vector on inclined plane. Now, look at this. And we have a force that is weight down here. This is theta. And we want to resolve the weight along the plane, along the inclined plane. So, which means that we are going to develop two perpendicular forces that will be equal to the weight. What happens? We have this like this, and then we have another one parallel to the plane like this. So, the two of them will be equal to this weight. Let's look at it very well. This is theta. This place will be 90 minus theta, because this place is, so for everything to be 180. And if you look at it, this place to this place is 90. Therefore, 90, this place will be 90 minus theta. This place. Therefore, we have 90 minus 90 plus theta. So this place is giving us theta. Can you see now? So we have this force now. Let us now turn this to make it look easy now. Let this plane, let us make it look like x axis. Let this one, let us make it look like this. And then this one, this is our W now, because this is the W. Can you see? And this place is parallel to this plane. So this one, and this one, the perpendicular one, let me call this one P, let me call this Q. So the perpendicular one, and this is the parallel along the plane. So we have this place to be theta. So if you look at it, this place is Q is W sine theta, and P is W cos theta. Can you see the application of the resolution of vector now? We look at another one now. Let's look at another one. We have a force P pressing on an object on the inclined plane. I want to resolve this P along the plane and the perpendicular to the inclined plane. If you look at it, this one comes here. This place will give us alternate angle. This place will be theta. And let us draw another perpendicular. This one. So what do we have? Along the plane, we are going to have P cos theta. Perpendicular to the plane, we are going to have P sine theta. So just understanding these facts will help you to solve so many problems with ease. You can also look at it like this. If you have a plane like this, and you have a force or anything, either present on it or away from it, giving you beta here. With our work now, you can easily see that this place will be, let's call this one V. The result, the component of V along this place will be V cos beta, and this one will be V sine beta, because it has already subjected the angle along the plane already. It is already from the plane. But sometimes they might give you this angle to the parallel like this and tell you that it is gamma. So what you just need to do is to subtract, because this place is theta now. This angle here will be gamma minus theta. So this place will just be V sine gamma minus theta. This place will be V cos gamma minus theta. So these are just the simple application of the this. When we get to the next section, you will see better and bigger application of resolution of vectors. Now let us look into addition of vectors again. You know, we talk about vectors like this. We want to add two vectors. Theta 1, theta 2. And this is V1 and this one is V2. And we said if we want to add this one, we just need to do something like this. V1. And then, to make it easy for us, just make a plane like this. A plane like this. For V2, bring a plane to carry. This one will be V1, theta 1. This one too will be V2, theta 2. Just make it like you are carrying different planes. You will see how easy it will be easy. How convenient it will be for you to do the summation of your vectors. Consider each one like they are in a plane separately, and you put it like that. Sometimes you might be asked, okay, like in bearing, when one goes like this one goes like this, what is the final destination? You can use this vector resolution to find the direction and the total distance in bearing. You know, that one deals with displacements most times. So just add like this. This is V1, theta 1. V2, theta 2, and then just break. So it will be easy. Depends on you. You can draw it straight and use cosine rule, or you can just say, okay, this is V1 cos theta, V2 cos theta, V1 sin theta, V2 sin theta. Then you will do the summation, that is V total. So V total is equal to V1x, that is V1 cos theta, plus V2x squared plus V1y plus V2y, that is the vertical. You square root everything. You square root everything. And what will be the final direction? This one is going to be arctan V1y plus V2y over V1x plus V2x. So I believe that when you see that each one acts like they are in different planes and being joined, it will give you better understanding of the addition of vectors.